speaker. Today's speaker certainly needs no introduction. He's one of the most well-known condensed matter theorists today. He's also particularly known to many of us as his work has had profound influence on both theoretical and experimental studies being undertaken here at Stanford. His work has been recognized by a plethora of the most coveted prizes in the field. He won the Dirac Prize and the Oliver Buckley Prize, both of which he shared with our late colleague Su-Cheng Zheng. He won the Physics Frontier Prize and the Franklin Medal and the Frontiers of Knowledge Award, and most recently, the Breakthrough Prize in Fundamental Physics. His work has spanned many of the most interesting problems in condensed matter physics. I first encountered his work on doped holes in antiferromagnets in the context of high temperature superconductivity, and actually had the pleasure of working with him on one paper on the quantum Hall effect, a paper that I'm very proud of, in fact. But of course, his most famous work has been in the field of topological insulators and more generally on topology as an organizing principle in condensed matter physics. So, okay, without further ado, today's speaker is Charlie Kane.
Okay, well, thank you so much. Let me share my screen. Let's see, here we go. Okay, let's see if this works. Okay, good to go. So thank you so much, Steve. That was really a very kind introduction. It's really a pleasure to at least virtually be able to visit Stanford. I wish I could be there in person, but that's the situation we're in. So as Steve mentioned, topology and symmetry are two of the sort of grand organizing principles that we have for how we think about the phases of matter. And so symmetry, of course, allows us to distinguish phases according to the pattern of, symmetries that are broken. But topology is a very powerful tool that allows us to distinguish distinct phases that have the same symmetry. And so these are two big ideas. But over the last decade and a half, one of the lessons that we have learned is that the interplay between symmetry and topology is very rich and allows for a lot of understanding of the different kinds of quantum electronic phases of matter that can exist. And so what I want to talk about today is sort of a version of the interplay between symmetry and topology. And in particular, translation symmetry is what I'm going to be focused on. So translation symmetry and rich topological phases. And so this is going to be some work that I've been done over the last year or so, mainly in collaboration with my PhD student, Pak Man Tam. And so Pak, I think he's going to go places. He's a really bright guy, and I've been very proud of how he's been working out. So keep your eye out for him. So what we're trying to do is trying to understand, symmetry protected topological states with strong interactions. And so I'm going to introduce sort of a theoretical tool that we have, which is a coupled wire model. I'll describe that. And with that, we're going to describe a couple of classes of different symmetry-enriched topological phases that we can have. The last part of the work is going to be work that involved also, in addition to Pachman, Jorn Venderbos, who's a former postdoc of mine who's gone on to start an assistant professor at Drexel University, and so he's been involved in the latter part. So so let me sort of start off talking about symmetry and topology in band theory. Okay, and so of course the advent of topology and band theory first showed up with our understanding, celebrated by the Nobel Prize to David Thales, our understanding of the role of topology in understanding the integer quantum Hall effect. And so in the bulk of a two-dimensional electronic system, if it has an insulating gap, it can be characterized by a topological invariant called the Chern number. And when that is non-trivial, it's basically like a integer quantum Hall state, which has topologically protected chiral edge modes on the boundary, which are these one-way propagating edge states that propagate on the boundary. And so there's this interplay between the bulk and the boundary that is dictated by the topology of the quantum state. So the quantum Hall effect is really all about topology. But when you have symmetry, you both lose things and you gain things. So if you have, in particular, time reversal symmetry, the symmetry that happens when you run a motion picture backwards, then of course that eliminates the quantum Hall effect. Okay, because if you run the motion picture backwards, then the edge state goes in the opposite direction. So you lose the quantum Hall effect with time reversal symmetry, but one of the things that we realized is that you get something new. You get the phenomenon of time reversal invariant topological insulators. And of course, at Stanford was one of the centers of the development for the theory and the realization of topological insulators. And I had many interactions with Xucheng Zhang, and I'm so sorry to that he had to leave us. So what happens in a two-dimensional topological insulator, the quantum spin Hall effect, is that you have an insulator on the interior, but on the boundary you have helical edge states, which are propagating in both directions, but in a sense their spin is flipped, and they are protected by the Kramer's degeneracy that happens right at when these bands cross, that are protected by time reversal. So this can happen in 2 dimensions. It can also happen in 3 dimensions at the surface of a strong 3-dimensional topological insulator. You have 2-dimensional helical surface states. Okay, and so these are topological electronic phases within band theory that are protected by time reversal symmetry. In band theory, there's another symmetry that's interesting to think about, which is the particle hole symmetry that occurs in the sort of mean field description of a superconductor. So that allows for the possibility of a topological superconductor, which has a superconducting gap in the interior. And in 1 dimension, what can happen is at the end, you have a state that's exactly at 0 energy, and this is called the Majorana state. Okay, and so this Majorana 0 mode exists at the end of a 1-dimensional topological superconductor. Okay, and so these are all kinds of states that are protected by either time reversal or a particle hole symmetry. Now, one of the things, there are a lot more symmetries that you can think about, and in particular in a crystal, there are many different kinds of symmetries, and I want to focus on one, which is translation symmetry. And so one of the things that translation symmetry leads to is what we call a weak topological insulator. Okay, and this is one of the things that we realized when we first started thinking about realizing there could be such a thing as a 3-dimensional topological insulator. What we realized that in addition to the Z2 topological invariant that distinguishes a strong topological insulator with the helical surface state from from a trivial insulator, we realized there are actually 3 other Z2 topological invariants that characterize a 3-dimensional band structure. Okay, and so these other 3 are the weak topological insulator invariants, and what they and a weak topological insulator, the way you can think about that is it's basically a stack of two-dimensional topological insulators. Okay, so if you just have a bunch of two-dimensional planes and you stack them on top of each other, and I'm sorry, my phone is ringing. If you stack them on top of each other and you make a three-dimensional material, then on the side surface, there will be a edge state. You'll have the remnant of the one-dimensional helical edge states. And so they will form on the side surface, they will form a sort of a quasi one-dimensional electron gas. And this is still protected by time reversal symmetry, but it's not as protected as the helical surface state, the two-dimensional helical surface state, which just has a single Dirac point. This has sort of two Dirac points inside the Fermi surface, okay? But, you know, this weak topological insulator is more interesting than you might first have thought. So it turns out it's protected by the translation symmetry, translation by one layer. So if you have the this surface state, you can open a gap on the surface by lowering the symmetry and dimerizing it. So you can pair up the different pairs of layers, and you can pair them together, and the helical surface states sort of kill each other, and they open up a gap on the surface. But the thing that's interesting is there are two ways you can do this, and this is something that Xiaoliang and Xucheng noticed was interesting. That if you have a boundary between these two, then that has a protected helical mode that lives on it. Okay, so there's this sort of interesting interplay between the symmetry, the translation symmetry, because of course these A and B phases are related by the translation symmetry. And so there's an interesting interplay between the translation symmetry and the topologically protected helical modes. Okay, and so so weak topological, we've known theoretically about weak topological insulators for 15 years. There's actually a relatively recent experiment where people have seen evidence of a weak topological insulator in bismuth iodide. So it's Bi4 iodide 4. And so what they do, angle resolved photoemission spectroscopy on the top surface as well as the side surface, and they see evidence that there's nothing on the top, but they have a quasi one-dimensional, Fermi surface on the side surface. And so, so this weak topological insulator is something which seems to actually exist. Now, another translation symmetry protected topological phase you can contemplate is a superconducting version of this, a weak topological superconductor. And so this is like so if I have a one-dimensional topological superconductor, it has the Majorana mode at the end. So allow me to take a stack of those to form a two-dimensional material. Then the Majorana modes at the end will then form a chain of Majorana modes, which is just like the one-dimensional Kitaev chain, which is a model of a one-dimensional chain of Majorana zero modes. Okay, and so this will form a one-dimensional non-chiral Majorana mode on the edge. Okay, but again, it's going to be gapless. It's because the translation symmetry guarantees that this Majorana chain is undimerized. Okay, and of course, what Kitaev realized is that if you dimerize the Kitaev chain, then you can form a gap. But there are two ways of doing it, and on the boundary between those two, you'll have a unpaired Majorana zero mode. Okay, and so this is a interesting, translationally symmetry protected state. Another thing that that can happen in this situation is another interesting interplay between the translation symmetry and the topology is that if you have a defect due to the translation symmetry, namely a dislocation, which is a point defect around which you translate by one step, okay, which is the Berger's vector, then if just by looking at the picture, it's pretty obvious that this one-dimensional topological superconductor ends, and it'll have an unpaired Majorana mode. Okay, and so a dislocation in this weak topological superconductor binds a zero mode. And so so I'm not aware of any experimental systems that have realized this yet. I think it would be something interesting to do. There have been suggestions. So in particular, if you can have a quasi one-dimensional superconductor, and there's an old suggestion by Steve Kivelson and Raghu that strontium ruthenate forms, could form chains and have superconductivity, which has a one-dimensional character. And Xiaoliang Qi and Taylor Hughes pointed out that that actually then relates to this weak topological superconductor. Okay, so that's one potential, route. I'm not sure what the current status of that proposal is at this moment, but that's an interesting idea, and maybe there are things that are like that we could find. Another, route that one could take is possibly to start with the surface of the weak topological insulator. Okay, which we sort of know that exists now. If you proximatize that with a superconductor, then that forms a two-dimensional superconductor that's sort of like this. Okay, it's not exactly the same as this, but it's sort of this superconducting state would be as to the weak topological superconductor as the surface proximatized strong topological insulator is to the P plus IP superconductor. So it's the same sort of relationship. Okay, and so I think it's not too far out of bounds to think about that these might be things that could be possible to realize in the real world. Now, what I want to focus on in this talk, though, is so this is all within the context of band theory. So I want to try to seek generalizations of this kind of symmetry protected topological order in a strongly correlated system. Okay, and in strongly correlated systems, we don't have the luxury of band theory. Okay, which is a really wonderful, simplification that allows you to do all this rich topological analysis. So we need to do something else. And so how can but that said, we do know that there are many classes of very rich topologically ordered states when you allow yourself to have strong interactions. And of course, the hallmark of that is the fractional quantum Hall effect. Okay, and so how do we understand the fractional quantum Hall effect? And of course, that all goes back to Laughlin, of course, who wrote down his wave function in the lowest Landau level. And by understanding his wave function, Laughlin was able to understand the essential features of the Laughlin state, which is that it is an incompressible fluid with fractionally charged quasi-particle excitations. Okay, and so Laughlin was basically able to understand almost, most of what is important about the Laughlin state. But there's a question how one can generalize that understanding and how one can understand, instead of as a wave function, how can one understand the Laughlin state as a macroscopic phase of matter? Okay, and a root, it's sort of in the same way that we understand a superconductor as a macroscopic phase of matter, which we can understand in terms of a Landau-Ginzburg type description. And the effective field theory of the fractional quantum Hall effect. This was introduced by Shucheng and Steve long ago, as well as many others contributed to this. So the effective field theory description as a macroscopic phase of matter of the fractional quantum Hall effect has the form of a two plus one dimensional topological field theory. In particular, it's a Chern-Simons topological field theory. And now in both the sort of wave function description and the low energy field theory description, there's an important connection to conformal field theory. Okay, so in particular, for the wave functions, Moore and Reed made the observation that the Laughlin wave function can, the wave functions in the lowest Landau level, which is what the Laughlin wave function is, can be understood as correlators in a two-dimensional conformal field theory. Okay, and now of course, what this allowed Moore and Reed to do is it allowed them to contemplate generalizations of the Laughlin state based on what is known about different kinds of two-dimensional conformal field theories. So in particular, it allowed them to invent the Moore-Reed wave function, which describes the Moore-Reed state, which is the first non-abelian state, a quantum Hall state that we came to understand. Okay, and so this led to, of course, a lot of new understanding. Now, of course, conformal field theory also shows up as the theory of the boundary of the the edge states of the fractional quantum Hall state. And so in particular, the boundary of a Chern-Simons theory is a chiral Luttinger liquid. Okay, and so this was, of course, introduced by Wendt. Now, now what I want to be able to do, though, is I want to be able to somehow talk about these within the context of some translation symmetry protected state. I want to be able to apply this. It's kind of, for the wave functions in the lowest lambda level, it's a little bit hard to, do this in a crystal, right? Where one has atoms and, band structure, okay? Whereas the effective field theory, one drawback of this is that when you write this down, you sort of have lost sight of the original electrons. Okay, so the original degrees of freedom are sort of hidden in this low energy effective field theory. And so what I'd like to consider is sort of a bridge between these two approaches, something which makes contact to the field theory, but also has within it at least some contact to the original electrons. And so this is what this coupled wire construction can do. And so I sort of view it as a kind of a bridge between the sort of microscopic electronic theories of the electrons and the effective field theory. What makes this work is the fact that there is a precise connection between the electrons and the field theory in one dimension, which is the subject of one-dimensional bosonization. Okay, and so so this wire construction is going to be a venue where I can formulate a precise theory of these symmetry protected states. And so I want to introduce you to this wire construction a little bit. And so what it basically is, and I'll say that the wire model doesn't really teach us things that we didn't already know based on the wave function or the field theory, but it gives us another way of arriving at the same physics. And so what I want to imagine is I have a bunch of one-dimensional wires arranged in a array, two-dimensional array like this, and I can put them in a magnetic field. And so let's first think about the case where the electrons are just non-interacting electrons with p squared over 2m Hamiltonian. Now, of course, in the presence of a magnetic field, I can describe that with a vector potential. And what that does is that each wire, it shifts the momentum of each wire, over because of the vector potential. Okay, and so this gives an interesting situation where you have these band crossings. Okay, and the band crossings are between states on one wire and states on the next wire. And so if you allow tunneling between the wires, then that will lift these degeneracies. And you can immediately see the emergence of Landau levels as well as the edge states. Okay, so you open up a gap at all these crossings, but of course this one gets left behind. And so this is really just like the Landau levels. And so the way you can think about this is, let's focus, and if you if you have the Fermi energy in here, then this is really at the filling nu equals 1, where there's 1 electron per quantum of magnetic flux. And so at this filling factor, these band, the low energy states at this energy, you can sort of view each wire is going to have a state at plus kf and minus kf. So those are right movers and left movers. And so I can describe that at low energy by a theory of right moving and left moving electrons. And then the right mover on one wire can connect to the left mover on another wire. And so that I sort of drew that as a little arrow connecting these. And that opens up an energy gap, basically killing these. And so you can immediately from this picture see that you're going to be left with a chiral edge state on the boundary. Okay, and so this is a very simple-minded, way of arriving at the integer quantum Hall effect. Okay, and this was actually pointed out by Shivaji Sandhi and Kun Yang, some 20 years ago. And so the question is, can we come up with a similar description of the fractional quantum Hall effect? So what happens if we're at filling nu equals 1/3? So now I have 1/3 as many electrons. And so if I do that, then of course my Fermi energy is going to be down in the bottom here. And so an electron, a right moving electron on this wire can't just jump over to here without violating momentum conservation. Okay. But if the filling is exactly 1/3, then there is a multi-particle process that conserves momentum. Namely, I can take an electron and I can move it over to here. And at the same time, I can backscatter a pair of electrons. Okay, and that backscattered pair exactly makes up the momentum if I'm at filling 1/3. And so this is a allowed scattering process. And I can represent that with this little cartoon here, where I tunnel an electron and I backscatter a pair of electrons. Okay, and so the way I can think about what I'm doing here, so I can write down a model where this is what I'm using to couple these wires, and I can think of that I have a sort of a composite electron operator, which is my adding an electron plus some number of backscattering processes. Now, of course, this is a many particle interaction. Okay, and so we can't write down the band theory of this. Okay, but this is something that we can analyze using the power of one-dimensional bosonization. Okay, and so what we can do is so if we have a one-dimensional electron gas, so this is my same left movers and right movers. So it turns out that the low energy theory of this can be mapped exactly to a low energy field theory of bosons, basically. And so this is an exact mapping between the theory of right and left moving fermions and the theory of bosons. And the bosons have right and left moving, excitations as well. And the beauty of this one is that you can make an interacting electron gas with an interaction between the right and left movers, but it remains a non-interacting boson theory. Okay, and so it's a free field theory of bosons, and so this is the content of bosonization. And so when we do this, though, so this introduces an interesting parameter, okay, which is the interaction. And this interaction is often characterized in terms of what's called the Luttinger parameter K. And so K is a parameter which describes the strength of this interaction. So it's equal to 1 for non-interacting electrons, okay? But when K is not equal to 1, then if we sort of diagonalize this Hamiltonian to express it in terms of right and left moving chiral boson modes, then the original electron operator sort of mixes, it excites both right and left movers. But something very special happens at a very particular value of this Luttinger parameter. Okay, so when this Luttinger parameter is 1 over a odd integer, is 1 over m, then precisely this this correlated composite electron operator, which is adding an electron and doing some backscattering, it becomes it couples only to the right moving chiral boson. Okay, and so this is for this particular value of K. And so what that means is that if I write down for this, so if I dial up my interaction to this value, then this theory where I couple my electrons like this, then what it turns into is something where I only couple the left movers on one wire to the right movers on the next. Okay, and so this looks exactly like what I did in the integer quantum Hall effect. And so these are going to pair together and they're going to kill each other, okay, leaving behind a undisturbed chiral edge state. Okay, which in this case is going to be described by a chiral Luttinger liquid. My claim is that this is really a faithful description of the Laughlin state. So in particular, the way we describe this coupling, so it's going to end up being a cosine term. Okay, so the electron operator is the exponential of the chiral boson, and so we get the cosine of this variable that I called capital theta. And so when this parameter is very large, then capital theta is basically just going to be locked at some multiple of 2 pi over m. And that means that we open up a bulk energy gap. Okay, and so we have a gap in the bulk, and we have a chiral edge state, and that has the character of a quantum Hall state. Now, even more, we can use this to understand the presence of a Laughlin quasi-particle. Okay, so since we have a cosine, we can there's going to be a low energy excitation which lives in between the wires, which is a kink where this variable theta jumps from one minima of the cosine to the next. Okay, and that will have precisely a charge 1/3 in the 1/3 quantum Hall effect. This is the Laughlin quasi-particle. Okay, and so this is the way we understand the Laughlin state in this coupled wire construction. And now, so what's going on here?
Charlie, how about the statistics? How do we see the statistics?
Yeah, I'm gonna mention that. That's my next point. So what is allowing this to happen? Okay, what is allowing this to happen is that we have one theory, which is a theory of a one-dimensional electron gas with interactions, at Luttinger parameter 1 over m. Okay, and that one-dimensional electron system has a low energy spectrum of excitations that is identical to the low energy spectrum of excitations of a strip of nu equals 1 over m Laughlin state. Okay, so of course the strip has low energy edge states, but the structure of the low energy Hilbert space of these two is identical. And so the reason the wire construction works is because if I take a bunch of these, basically what I'm doing is I'm taking a bunch of these strips and I'm just gluing them together to form a two-dimensional system. I'm gluing them together by tunneling electrons between the sort of nearby edges and sewing these strips back together. So it's the identity between these that, this exact identity between the one-dimensional Luttinger liquid and the strip. And what these both are is they're both described by a rational conformal field theory. Okay, so this is a little bit fancier, jargon to use, but so these are both described by the same field theory, basically, and that's the field theory of a free boson that is compactified onto a circle. Okay, and the circle the radius of this circle basically determines the Luttinger parameter k. Okay, and so what we see from this is that at least for a particular sequence of these radii, when the square of the radius is 1 over an odd integer, then we can sew these one-dimensional systems together to form a two-dimensional system, which forms a two-dimensional quantum Hall state. Okay, and in particular, to answer Steve's question, it's important, so this rational conformal field theory, it has a Hilbert space which sort of factorizes into left and right moving sectors. So they're left moving states and right moving states, but they're not completely independent of each other. Okay, they are tied together in a particular way because so for the edge states, the Laughlin quasi-particle can't be created by itself. Okay, the only way you can get a Laughlin quasi-particle to the top edge is to move it from the bottom edge. Okay, and so the Hilbert spaces are not independent of each other. Okay, the number of Laughlin quasi-particles the total number has to add up to 0. Okay, or some multiple of m, because I could add electrons. But there is a allowed operator which tunnels a Laughlin quasiparticle from the bottom edge to the top edge. Okay, and so this is an allowed operator in the theory, okay, which takes a quasiparticle on the bottom and it deposits it on the top. Okay, and so it's the same quasiparticle on the bottom as it is on the top, and that's what the meaning of this word diagonal is. And I'm going to come back to this in a little bit. So the fact that this is a physical allowed operator, it has to have a corresponding operator in this system, and this is just the operator that backscatters an electron from the right mover to the left mover in terms of the original electronic variables. Okay, and so this is certainly an allowed operator in the Luttinger liquid theory, and that becomes this quasiparticle backscattering operator. Now, with this quasiparticle backscattering operator, then we can answer Steve's question about the statistics, because now I can imagine I have a quasiparticle here. Now, of course, this quasiparticle is a kink in theta. So it's say theta is equal to 0 on one side. It's 2 pi over m on the other side. I can take another quasiparticle going around using this operator. Okay, and it's not too hard to see that if you do that, then you pick up precisely this phase 2 pi over m, which is the fractional braiding statistics that the Laughlin quasiparticle exerts. So sewing these one-dimensional conformal field theories together to form a two-dimensional topological field theory, understanding these quasiparticle operators allows us to characterize the sort of topological data that characterizes the two-dimensional state, namely this braiding phase. Okay, so
John,
look,
I'm still a little bit confused. I mean, I'm sure that it's a simple. I mean, it's obviously the right answer, but I'm having a hard time visualizing something. So this quasiparticle is a kink in the white region.
Yes, exactly. That's
and
right.
How do I visualize moving a kink from one white region to another? Doesn't it?
Well, let's keep this kink. Now, of course, this one is going to have a kink as well.
No, when I tunnel, you start with the lower right-hand blue dot.
Yeah. So I'm going to go up, and around. So when I claim, so I'm going to do the first one. The first one I'm going to do by using, phi right minus phi left here.
I understood in terms of that. I just didn't understand it. I had pictured this as being Peloton in the.
I can't hear you. No, I was listening.
I'm sorry, Steve. Could you say that again?
Yeah. So I picture there being a kink in the theta field at the position of that lower blue thing.
Yes.
The lower right hand one.
Okay. And
then when we tunnel, what happened? There was a kink there. How do I remove a kink, because a kink propagates to infinity?
Yeah, well, so I think so you have to sort of think that theta is kind of a compact variable.
Right.
Okay, so the kink just lives. Yeah. So right. So I think.
Oh, forget. Maybe I shouldn't distract you now.
Right. Yeah. So right. The kink does move, but I think you have to think in terms of theta being a compact variable, but it is it does pick up the this theta when it goes across.
Yeah. I mean, in terms of your operators, I understand it. I'm just visualizing the kink I'm having trouble with, but okay, I'll think about it. Thanks.
Yeah. I mean, look, this dashed line here is unobservable.
Right.
Okay. So in fact, I could do a gauge transformation and move the dashed line over to the other side.
Right.
So there's no meaning of the value of theta.
Yeah.
They are all, theta and theta plus 2 pi over m are the same.
Yeah. Yeah.
Okay. That's the point, I think.
Yeah.
Just to clarify the same point, I think when you move the quasiparticle, the operator that moves the quasiparticle is local, right? So
yes,
when you sit
exactly.
far away, it doesn't really do anything that local.
Yeah, exactly. Yeah, good. Okay, thanks. So look, okay. So now the question is can we can we generalize this? Okay, so now I've discovered the fractional quantum Hall effect. You know, if only I'd done it, you know, 40 years earlier, then. But so one way one can go is one can ask, well, are there other conformal field theories that one can generate in this way? You know, maybe non-abelian conformal field theories. So we could do you know, wire constructions for the non-abelian, you know, quantum Hall states. I want to do something simpler based on just a simple observation, which is that you know, the free boson, you know, this Luttinger liquid conformal field theory, it's a conformal field theory for any value of k. In particular, it's a rational conformal field theory, meaning that it has a finite number of, you know, sort of quasi-particles. It's a rational conformal field theory for any rational value of k, or of the radius. Okay, and so so the question is whether those could correspond to physical states or not. Now, if you look up in the big yellow book about this, you know, free boson compactified on a circle, you learn some word that actually, if it's not 1 over an integer, then it's called a non-diagonal conformal field theory. So then there's a question: if these are real physical states, what's the meaning of that? And I'm going to try to explain this, and explain that this actually has something to do with the symmetry protected topological order, similar to a weak topological superconductor. Okay, so good. So it's actually not so hard to generalize this wire construction to a rational value of k. Okay, we could just consider a more general tunneling operator, where instead of just tunneling 1 electron from wire to wire, we tunnel p electrons, along with some number of backscatterings. And so this defines then, you know, a p and a charge p and a momentum q, if you will. And this operator will be purely chiral when this Luttinger parameter is equal to p over q. Okay, and so we can do exactly the same construction with this composite, p charge pe a composite tunneling operator, and we'll be left with, you know, a gap in the bulk. Okay, if this cosine is big, theta is going to be pinned, and we'll be left with some chiral edge state. Okay, a single channel chiral edge state. And so we have some state, and the question then is, what is this state? And I'll say that this composite tunneling operator, it conserves momentum at filling p over q. Okay, so what is this? So first, let me tell you what it is not. It is not the familiar fractional quantum Hall states at like nu equals 2/5 or 3/7. Okay, those states are something are different. Those states are sort of multi-component Laughlin states, whereas this is a single component state. Okay, so it's not those.
I'm confused about one stupid thing. What's k?
K is the number of backscatterings.
And how's that related to q?
What? Yeah. So k. Yeah, I'm sorry. I should have.
Oh, I see. It's over there.
So Q is equal to P plus 2K. Yeah,
okay,
sorry.
Good.
Yeah, sorry. I should have been specific about that. So,
yeah,
right. So it's not the sort of multi-component quantum Hall states. Another thought you might have is that, you know, you could also imagine a Laughlin state built out of clusters of p particles. So you can imagine, let's glue all of the electrons together to form charge pe particles, and they'll either be bosons or fermions, depending on whether p is even or odd, and then form a quantum Hall state out of those. Okay, and so that actually looks similar. So one thing, so the kinks in this are going to be charge e over q quasi-particles, and it has it's the Hall conductance is going to be p over q. And so this strongly clustered state sort of gets this right, okay? So if you have charged PE particles at filling 1 over P times Q, then the Hall conductivity is going to be 1 over P times Q times P squared, so it's going to be P over Q. And the charge of the sort of smallest Laughlin quasi-particle is going to be 1 over PQ times P. Okay, so that sort of works. So this state sort of smells like the strongly clustered state. Okay, and in fact, I wrote down this wire construction 20 years ago, and I wrote down this state, and so I assumed that that's what this was, and lost interest. But what I realized more recently is actually they're not quite the same, and this one's a little bit more interesting. Okay, and so let me try to explain to you the sense in which this state is not the same as the strongly clustered state. And one difference that you can obviously see is that this state actually has electrons in it. I could add an electron to this wire, whereas in the strongly in the strongly clustered state, I'll say I can't. So let me try to explain this. So unlike the strongly clustered state, the minimal this charge E over Q quasi-particle, the smallest quasi-particle I can make, there's no way that it can jump across a wire. Okay, and one way of seeing that is to notice that a Laughlin quasi-particle is associated with a quantum of magnetic flux. Okay, H over E quantum of magnetic flux. Okay, which of course and whereas in this case, the charge E over Q quasi-particle is going to be associated with a quantum of flux H over P times E. Okay. Now, if all that I had in my system were charged PE particles, then that would be the quantum. The quantum would be of flux would be fractionalized, and tunneling a H over PE flux would be a local operator. But if there are electrons, if it's possible to have unclustered electrons, then those unclustered electrons are non-local with respect to this H over PE flux. Okay, and so if there are non-local electrons, then it's like this this tunneling this, trying to tunnel this quasi-particle across would create like a string, like a Jordan-Wigner string that extends off to infinity. So it wouldn't be a locally defined operator. Okay, so another way you can sort of see this is, you remember how I said we could tunnel electrons. Well, it's just the psi right dagger, psi left of the original wire. But in this case, if I write down the psi right dagger, psi left, which is guaranteed to be a local operator because it's made out of the original electrons, then that doesn't tunnel a minimal quasi-particle, it tunnels P of them. Okay, and that makes sense because this is like tunneling an H over E, which is allowed, which is local, no matter what. Okay, and so so this means that you can't just move the quasi-particles around in the same way. Okay, so there's a difference. But these quasi-particles, they still could be there, and in particular, you could make one of these quasi-particles by just adding an electron. Okay, and so in particular, so it turns out that that if you choose an integer r correctly, if I add some number of electrons, then I do add a minimal quasi-particle on one side, and all the rest of the charge is on the other side. So this is a perfectly well allowed operator, and and it makes sense because when you do the Luttinger liquid. If you just have a regular Luttinger liquid with some value of K, if you add an electron to that, then some of the electron goes into the left moving chiral sector and some of the electron goes into the right moving chiral sector. That's exactly what this is. And so if I add R electrons, then it's possible to have precisely the E over Q go into this. Okay, if I do the wrong thing, then maybe I'll have more than E over Q go into one and the other. But if I do R, then I can get a minimal quasi-particle into here. Okay, and so this means that in this one-dimensional thing that I'm going to stitch together, I have right and left moving Hilbert spaces, but the right and left moving chiral sectors are stitched together in a different way than they were in the Laughlin state for the K equals 1 over M states. Okay, they're not coupled together in this diagonal way where the states are paired and I can pick up one quasi-particle and just put it on the other side. they are paired together in a non-diagonal way where there's a local operator that picks up one quasi-particle and puts down a different quasi-particle. Okay, and so this is what it means to be non-diagonal. Okay, so in fact, the chiral Hilbert spaces of this state that I'm constructing and the strong paired state, they're the same. They're just the charge E over Q quasi-particles, but it's the way that they are sort of glued together that is different. Okay, and that's what this non-diagonal means. Now, the fact that a quasi-particle can't move by one doesn't mean that it can't move. Okay, because it could move by two. Okay, because what I could do is I could move it by one, and of course that screws up this middle here. But then I could move it again, and that undoes what happened in the middle. But what I had to do is I had to tunnel R electrons from one wire to the next. Okay, so if I do that, if I do this, picking up R electrons from this one and depositing them on the next wire, then what that accomplishes, it accomplishes moving a minimal quasi-particle from here to here. Okay, and so whereas the quasi-particles cannot hop by one space, they can hop by two. And so they can move around. So they really are deconfined. They can explore the entire two-dimensional plane once I sew these wires together by tunneling electrons between them. Okay, and so so these really are quasi-particles. But now this quasi-particle, it can move around, but it can never get to the odd sites. Likewise, the odd quasi-particles, they can move around. They can never get to the even sites. So now we have two different kinds of quasi-particles. We have the quasi-particles that live on the odd links and the quasi-particles that live on the even links. Okay, and so this is the difference between the topological order of this non-diagonal state and the topological order of the strongly clustered state. Okay, so so what does this mean? So you can then ask the question, well, we have these two different kinds of quasi-particles. Can we characterize the topological order by characterizing the braiding statistics that they have? And so you might realize that it makes a difference. So if I have one quasi-particle going around another, it makes a difference whether or not the odd quasi-particle is going around another odd quasi-particle or it's going around an even quasi-particle. And so this is something you can work out. And so you can characterize this topological order. It's sort of like a combination of two topological orders. So the phase that one quasi-particle picks up when it goes around another. So there's one phase which is just like the phase that a Laughlin quasi-particle would pick up if it's in a state at nu equals 1 over p times q, this strongly clustered state. Okay, so certainly if an even quasi-particle goes around an even quasi-particle, that's what you should expect. Okay, but it's different going around an odd quasi-particle, and so there's a difference here. And so the even and the odd quasi-particles have a contribution which looks exactly like the contribution from a toric code. Okay, a ZP toric code. So the toric code is a model which goes under various names, which has two different kinds of particles, E particles and M particles. And for ZP, if you take E particles together, they're the same as nothing, and same thing for M of them. So for a Z2 toric code, which is like Kitaev's original toric code model, then 2 E particles is nothing. Okay. But it has the property that an E particle going around an M particle picks up a ZP phase. Okay, and so that's exactly what is happening here. Is that the quasi-particles of the non-diagonal state, okay, of this state that we're constructing in this wire construction, they're like Laughlin quasi-particles of the strongly clustered state, which just behave like all Laughlin quasi-particles do, but they are combined with either an E particle or an M particle of this Z2 toric code, E or M, depending on whether you're on the even links or on the odd links. Okay, and so so this is the way we can think about this, the sort of topological order that now this two-dimensional state has. Okay, it's like sort of a combination of Laughlin and a ZP toric code. Okay, so so given that though, there's something, so of course, we're used to people who know about toric code know about toric codes, and there are various situations where these can arise, but we have this a kind of interesting situation where the E particles and the M particle, they're really kind of the same, right? Because the E particle is just like an M particle on the other sublattice. Okay, and so the E and the M particles are related by symmetry. Okay, and so what we have is, so the E and the M particles, they're abelian anions, but they are related by an anionic symmetry, which is the translation. So if I do a translation by one layer, the E particle becomes the M particle. Okay, and so they're guaranteed to be exactly degenerate, and they're related by symmetry. And so this can leads to some new kinds of things, which I think maybe you'll sort of recognize have the same flavor as the weak topological superconductor. Okay, so in particular, if you have a dislocation, okay, let's allow ourselves to imagine that one of these wires ends. Okay, then if I move an E particle, now of course an E particle can always only move by two spaces, so I can move it up and I can move it along, and I can move it by two here, then move it back by two. When I've gone around this dislocation, the E particle has turned into an M particle. Okay, and so this dislocation sort of acts on the anions by implementing this symmetry. This dislocation acts like a non-abelian, defect. Okay, and so in particular, this is, so it's going to be a non-abelian twist defect. And this is the same kind of thing. So Shaliang and Mason Barkeshli had this theory a while back about bilayer fractional quantum Hall states, sort of like a parking ramp of quantum Hall states, where they considered similar kinds of defects like around the parking ramp, where one layer turns into the other layer, and they call them Genon defects, and they have a similar kind of non-abelian twist defect that can arise in those. And in particular, so it's worthwhile to distinguish the case. So the case P equals 2, where what we're doing is we're talking about pairing. So we're tunneling pairs of electrons, and so these are sort of like paired quantum Hall states, and this non-abelian defect, it's really just like a Majorana mode. Okay, and so that's sort of what happens when P is bigger than 2. Then it's like a ZP parafermion mode. Okay, so this is what happens at a defect. You could also consider what happens if you have the edge. And in particular, of course, if you have the edge on the bottom, this bottom edge breaks the translation symmetry. But if you have an edge that respects the translation symmetry, then you have a symmetry respecting edge of your toric code, basically, where the E and the M are the same. And so one thing that one can check with this is that if you have the edge of a toric code where you have the anionic symmetry between the E and the M, then there is sort of there's a parafermion chain at the end. So for P equals 2, it's a Majorana chain, just like the edge of the weak topological superconductor. And for P bigger than 2, it's going to be a undimerized parafermion chain. Okay, and so this is something that happens at the symmetry preserving boundary of this. So this kind of has the flavor of the weak topological superconductor, and actually, so let me go back and think about the weak topological superconductor a little bit more. So it's interesting to talk about vortices in a topological superconductor. For a regular topological superconductor, a vortex binds a Majorana mode. And so you can sort of view that as like being a non-abelian particle if you allow your vortex to be a dynamical particle. Now, of course, in order to do that, you need to gauge the electromagnetic field and include vortices in your Hilbert space, okay? And if you do that, then let's think about what happens in the, then these H over 2e vortices become topological quasiparticles, okay? And I claim that they have exactly this property that they can only hop by an even number of layers, okay? Because if you try to hop a vortex across a one-dimensional topological superconductor, you get what's called the fractional Josephson effect, which is that, that basically what happens is that when you advance the phase by 2 pi, then a Bogolubov quasiparticle is created at the junction, okay? And so you can't hop a vortex without leaving something behind, okay? But you can hop a vortex by 2 spaces, because then you can tunnel an electron between the two, okay? And so it's exactly the same situation where now the vortices there are going to be 2 kinds of vortices. There's going to be the vortices on the even links and the vortices on the odd links. And they are going to be the E and the M particles of a symmetry enriched toric code. So it's the same sort of thing that happens there. And I see I'm running out of time. I have one more thing I want to tell you before I close, which is that so what we've done here. So this is sort of this weak topological superconductor sort of is to this quantum Hall state that I introduced. It's sort of in the same way as the P plus IP superconductor is to the Moore-Reed state. Okay, and they're sort of same kind of analogy. And so you can ask the question: could you have a insulating version of this? Okay, is there an insulator that has this same kind of symmetry enriched toric code order? And one way of thinking about that is that you can get to an insulator from a superconductor by condensing vortices, okay? And in particular, if you condense double vortices, then you leave the original vortices behind as topological quasiparticles. And so this is an old idea, dating back to the old days in Senthal and Fisher, that if you condense double vortices in an ordinary superconductor, then you get a Z2 spin liquid, or you could think of that as a toric code insulator, where you condense the double vortices, but you still have single vortices that remain as topological quasiparticles. The single vortex becomes the Boson of the Z2 spin liquid, whereas a Bogolubov quasiparticle, which picks up a minus sign when it goes around a vortex, is a neutral fermion, which becomes the spinon. And then if I combine the two together, the Boson and the spinon, I create a neutral boson, which is the E particle of the toric code. Okay, and so this Z2 spin liquid is a toric code, but it also, there's a charged particle as well. The electron sort of fractionalizes into a charge E boson and a spinon, and these are glued together by sort of a Z2 gauge field whose flux is the Boson. Okay, so the same thing arises if we condense double vortices in now this weak topological superconductor. So we get the same kind of topological order where I condense the double vortices. I have the single vortices remain, and so now I have even and odd Bosons. Okay, on the even and odd links, and those are like the E and the M particles of the toric code. And a Bogolubov quasiparticle is the neutral fermion. And now, of course, if I try to hop an E across, then I create to annihilate the M, then I create the fermion. Okay, so the fractional Josephson effect gives us the relation that E times M is equal to F. Okay, and in addition, of course, there will be the charge on as well. And so I think it's an interesting question to ask whether we could realize this symmetry enriched toric code insulator. And, so you might think that so in the wire, so we can write down a wire construction for this. I don't have time to sort of go into that. And what that suggests is if you can have a competition between sort of superconducting type order and charge density wave type order in a kind of a helical metal, that's the place to look for this. So maybe we could make something like this happen on the surface of a weak topological insulator, for example, if you're sort of in between a CDW and a superconductor. Okay, so maybe that's a place to look. So I think, so I don't have terribly good ideas of where to find this, but I think that's an interesting direction to go to. So I think I'm out of time. So let me just finish off and say that, when you have this translation symmetry and strong interactions, then that allows us to sort of contemplate something new, which is this symmetry enriched type toric code order, where the translation symmetry acts as an anionic symmetry. Okay, and somehow in this wire construction, this somehow made some contact to these sort of strange non-diagonal conformal field theories. Okay, and so look, I think there's sort of questions to think about theoretically, and maybe the more interesting questions are how can we actually make this come to life in the real world, so can we think about the fractional quantum Hall effect in anisotropic systems? One thought that I've played with is, you can make, these Moiré heterostructures, you can make them anisotropic. You don't have to have a hexagonal lattice. You can have a rectangular lattice, and that would give you some anisotropic Moiré pattern. Maybe you can populate that and come up with some, anisotropic fractional quantum Hall states in that. And again, I think that it's interesting to think about the competition between superconductivity and charge density wave order, and I know that's something that many people at Stanford have probably more expertise thinking about than I do, and so I'm looking forward to talking to people about that tomorrow. So I think with that, thank you very much. It's been a pleasure, and I'm happy to stick around for a while if people have questions.
Great. Let's. People can unmute for a minute to thank our speaker.
Thank you.
That was really very interesting.
Oh, thank you so much.
Are there questions? So maybe can I start with one?
Yes, absolutely.
So I'm just trying to understand the delicacy of the translation symmetry. So certainly, if I turned on some disorder or something, I would allow tunneling between the different wires that no longer satisfied the momentum conservation constraint.
Yeah.
So if I start from the decoupled wires, the moment I turned that on, I would be turning on presumably some lower dimensional terms that we might worry about. But I would think that once I've opened all these gaps, if I did it in the other order, if I first formed one of these states and then broke translation symmetry a little, I don't see how anything is very sensitively.
Yeah. So this is actually, so you could ask this question for a weak topological insulator as well. Okay. And this is actually something that we have sort of thought of. So if you think about, so of course, in that case, what's interesting is what happens on the surface. Okay. And
but nothing can happen in the bulk because you're gapped in the bulk.
Right, exactly. Right.
Yeah.
So on the surface, if you make it disordered, then I want to argue that there really is still something left, because so you could open up a gap on the surface. Okay, there could, but there are two ways you can do it, which are related by the translation. So if I open up a gap on the surface, if I just move everything over by one space, then I'll have a equivalent gapped state that is kind of the same. But if I have the domain wall between those two, then it has a helical mode. Okay, and so the upshot of this is that if you have disorder on the average, okay, so that you can't pick one sign of the gap over the other,
right? Then
you may locally open up a gap, but there's going to be just as much of one phase as there is of the other phase.
Mm-hmm.
And so you're going to have a network of domain walls. Okay, and so for the surface of the weak topological insulator, then there will be some it's like a Chalker-Coddington network at criticality on that. Okay, and I think for the one-dimensional topological superconductor, I think if you have the disorder on the average, then you're forced to be at a critical point. Okay, where the boundary is critical. Now it may be in a different universality class. There may be, disorder is probably important, but I think you can be certain that if you have symmetry on the average, that the surface will not be gapped. Okay, because how does it know which sign of the mass to have?
Yeah, I mean, I guess you could imagine though then that it can try to reconstruct, so it can be unhappy with.
Sure, you could spontaneously break the symmetry, of course.
Yeah.
Yes, yes, of course. Yeah,
I see.
Yeah.
All right, good. Are there other questions?
Well, if none of the specialists are asking questions, I wanted to ask if you could talk through a naive. I'm confused. So if I took your case and did a cylinder construction, so I presume I will have an even and odd effect. I mean, as I go around, one guy turns into the other, and that would.
Yeah. So if you have an odd number of chains, you're saying.
Right.
Yeah. Then going around, then it would be like there's a non-abelian flux going down the middle of the.
So I have to have a flux to account for that phase.
Yeah. That's right.
And then then it would have.
And I think and if you had the boundary of that, you would be guaranteed to have a zero mode.
You mean these?
Because you have. So let's think in the case where you have Majorana. So it's P equals 2. So it's like a weak topological superconductor. Then you'd have an odd number of Majorana modes at the end, and that's guaranteed to always have an exact zero mode. If it's odd, of course. So if it's even, then it won't be exactly zero.
Okay.
Yeah.
Thank you.
Can I ask a quick question? So you were working with free bosons at rational values of the radius squared, but it seemed like your construction was fairly general in that you could substitute compact boson with some other RCFT and sort of couple wires together in a similar way. Is that?
Yeah, well, that's one of the, I mean, I haven't done anything with that yet, but certainly there are lots of CFTs. And,
right.
So, and that's a path towards discovering things that you don't know. I mean, that, for instance, that's how Moore and Reed discovered the Moore-Reed state, is they recognized that that CFT was described the Laughlin state, and then Greg Moore knew all CFT, and so he was able to come up with something new. Okay, and so maybe there may be things there.
Yeah, I mean, I'm basically wondering because I don't know too much CMT, but I know some CFT, so I was wondering if there's opportunities to do stuff here. Did you have any expectations of what you'll get if you use, like, say, WZW models, or?
Well, you probably can get some non-abelian states. You could get non-abelian quantum Hall states, and of course, you might discover things that you already knew, that states that are already known. I think the new things that you're likely to get is you're going to have some interplay of the anionic symmetry. I mean, that's the thing that this construction gives that's a little bit different than the things that everybody already knows, is that the translation symmetry acts in a non-trivial way on the quasi-particles.
Got it. Thank you.
I guess from a solid state physics point of view, though, there would be a second question. I mean, getting these bosonized field theories on each chain is easy, starting with electrons. It's not quite so easy to get, to your starting point of your coupled chains. Yeah.
So
but for what you've done.
Well, I will say that you can get more exotic field theories by considering the couple chains. So for instance, if instead of a single component Luttinger liquid, if I consider, you know, sort of a Luttinger liquid with K flavors,
Right.
then I can get SU2 level K. You know, I can get SU2 level K.
Right.
You know, I can get Wess-Amino-Witten models, you know, within this wire construction. Now, from the point of view of solid state physics, you know, with the question is whether these can describe any real physical system or not, and one has to.
No, I mean, you can
think about that. But in terms of models that you write down, one certainly can use this wire construction to write down models that are at least in principle built out of electronic degrees of freedom, that then these more exotic conformal field theories emerge from. And so I think that is something that one could contemplate.
Are there more questions? Okay, maybe I have more questions, but I guess we're supposed to talk tomorrow. So
okay, good.
We'll let people go.
Okay, well, I look forward to chatting with people tomorrow, and thank you again for having me. It was a pleasure.
Let's thank Charlie again.
Okay, take care.